Welcome to Quiet Universe, where we explore the vastness of space, the depths of the ocean, and the wonders of our Earth with a calm curiosity. I'm glad you're here to join me on this journey through the cosmos, across the seas, and through the intricate layers of our planet. In the universe so grand, oceans so deep, and an Earth so complex, it's easy to feel small. But together, we can unravel the mysteries of the stars, the secrets of the deep, and the stories of our own world, finding our place within it all. Today, we're diving into the intricate dance of the universe, the cosmic web, the vast network that holds everything together. We'll touch on the cosmic flow that shapes large-scale structures, like the Laniakea supercluster, our galactic home, and the Great Attractor, a mysterious force drawing galaxies towards it. These are the threads and currents that weave the universe's story. The cosmic web is like the universe's hidden framework, a massive, interconnected network that binds everything together. Imagine looking at a city from above at night, seeing all the streets lit up, connecting neighborhoods with bright intersections where people gather. The cosmic web is a bit like that, but on a scale that stretches across the entire universe. In the beginning, the universe was more like a blank canvas, with just tiny differences in density scattered around. Over time, gravity started to pull matter together, and these tiny differences grew into the strands of the web. Think of it like pulling on strings. Wherever the strings cross, you get clusters of galaxies forming, kind of like the busiest parts of a city where roads meet. But just like in a city, not everywhere is equally busy. Between these strands are vast, empty spaces, almost like cosmic deserts, where there's very little going on. Meanwhile, along the strands, galaxies are slowly moving, drawn toward those busy intersections, merging and growing as they go. What's fascinating is that this web isn't something we can see directly. We only know it's there because of how galaxies are arranged and how they move. It's like discovering the secret paths and roads that connect everything, showing us that even in the vastness of space, there's an underlying order, a cosmic blueprint that tells the story of how everything got to where it is today. This underlying order is brought to life through a phenomenon known as cosmic flow. Cosmic flow describes the movement of galaxies and galaxy clusters across the universe, driven by the gravitational pull of matter. Over billions of years, this movement shapes the large-scale structure of the cosmos, creating vast clusters of galaxies, interconnected by filaments and separated by enormous voids. By studying cosmic flow, we can understand how these intricate patterns of galaxies and superclusters have formed, offering a glimpse into the dynamic history of the universe. It is constantly in motion, not just on small scales, but on the largest scales imaginable. This motion is known as cosmic flow, and it refers to the way galaxies and galaxy clusters move through space, driven by gravity and the distribution of matter across the cosmos. Imagine pouring syrup onto a pancake. The syrup doesn't spread out evenly. It flows along certain paths, pulled by gravity into thicker, more concentrated areas. Similarly, galaxies aren't scattered randomly across the universe. They follow paths shaped by gravity, flowing towards regions of higher density where matter is more concentrated. These movements create the large-scale structures we see in the universe today. These structures include vast clusters of galaxies, long filaments connecting them, and enormous voids where very little matter exists. Over billions of years, as galaxies flow along these paths, they create a kind of cosmic web, with dense regions where galaxies cluster together and vast empty spaces in between. Cosmic flow also explains why some regions of the universe are more densely packed with galaxies than others. It's as if the galaxies are being pulled towards certain destinations, forming superclusters like Laniakea. These movements are influenced by the gravitational pull of dark matter, which acts as an invisible framework guiding the flow of galaxies. For us, understanding cosmic flow and large-scale structure formation is like tracing the history of the universe. It reveals how the simple force of gravity, acting over billions of years, can shape the entire cosmos, creating the intricate patterns of galaxies and superclusters that fill the universe today. Now let's discuss the most mind-boggling aspects of cosmic flow and large-scale structure formation. Imagine the universe as an intricate, three-dimensional spider's web that stretches out over unimaginable distances. This web, known as the cosmic web, is not made of silk, but of galaxies, clusters of galaxies and vast regions of empty space called voids. At its core, the cosmic web is a network of filaments. These are thin, thread-like structures that connect different parts of the universe. Each filament is composed of both galaxies and dark matter, the invisible substance that makes up most of the universe's mass. These filaments stretch across hundreds of millions of light years, linking galaxy clusters in a delicate yet resilient structure. Within this web, galaxies are not randomly scattered, but are instead aligned along these filaments. The densest regions, where several filaments intersect, are home to massive galaxy clusters, the most gravitationally bound structures in the universe. These intersections act like hubs in the cosmic web, where matter accumulates and forms the largest and most energetic objects in the cosmos. Between these filaments lie vast voids, enormous, nearly empty regions where few galaxies reside. These voids are not just gaps, but are integral to the web structure, influencing how galaxies move and interact. The gravitational pull from the denser regions causes galaxies to flow along the filaments, moving away from voids and toward clusters. This cosmic web isn't static. It's in a constant state of evolution, shaped by the tug of gravity over billions of years. As the universe expands, the web stretches and the filaments grow thinner, but they also pull more matter into the densest regions, making the clusters even more pronounced. The concept of the cosmic web reveals how interconnected everything in the universe is, showing us that galaxies, including our own Milky Way, are not isolated but part of a grand, interconnected structure that spans the entire cosmos. Dark matter is one of the most mysterious and essential components of our universe. Although we can't see it, touch it, or directly detect it, dark matter plays a pivotal role in shaping the cosmos as we know it. Imagine you're an architect tasked with building a vast, sprawling city. However, the blueprints you're given are mostly blank, showing only a few landmarks and roads. This is akin to how dark matter operates. It's an invisible framework, a kind of hidden scaffolding that underpins the entire universe. Without it, the universe would look entirely different. Perhaps it wouldn't even exist in the structured form we see today. Dark matter makes up about 85% of the universe's mass, yet it doesn't interact with light or any other form of electromagnetic radiation, which is why we can't see it. However, its presence is felt through gravity. Dark matter's gravitational pull is what draws ordinary matter, things like gas, dust, stars, and galaxies together. Think of it as a silent but powerful force that shapes everything around it. In the early universe, after the Big Bang, dark matter began to clump together under the influence of its own gravity, forming dense regions. These regions acted as seeds, attracting the regular matter that would eventually form galaxies. Without dark matter's gravitational pull, these galaxies wouldn't have had the necessary conditions to form. They would have scattered, unable to coalesce into the structures we observe today. As time went on, dark matter continued to play its role in guiding the growth and evolution of the universe. Galaxies formed within the dense halos of dark matter, which provided the gravitational stability needed for them to hold together. Even today, the dark matter surrounding galaxies helps to keep them intact, preventing them from being torn apart by their own rotational forces. In the vast expanses between galaxies, dark matter creates an invisible web that connects everything together, influencing the motion of galaxies and the formation of larger structures like galaxy clusters. These clusters, containing thousands of galaxies, are some of the largest structures in the universe, and they owe their existence to the dark matter that binds them. So, while dark matter remains unseen, it is a fundamental force that shapes the universe's structure, acting as the unseen architect that designs and maintains the cosmos we inhabit. Cosmic flow is like the grand movement of the universe on a colossal scale. Picture yourself standing on a shoreline, watching how the tide pulls everything toward the deeper parts of the ocean. In space, galaxies experience something similar, but instead of water currents, it's gravity that's doing the pulling. Galaxies, including our own Milky Way, are constantly in motion, not just drifting aimlessly, but flowing along invisible pathways in space. These pathways are determined by the gravitational pull of massive structures in the universe, such as galaxy clusters and superclusters. These structures are like cosmic whirlpools, regions of higher density where gravity is incredibly strong. The concept of cosmic flow describes how galaxies are drawn toward these dense regions. Imagine being in a vast crowd, slowly being pulled toward the center of a busy square where the crowd is thickest. The closer you get, the stronger the pull becomes, guiding your movement. In the universe, galaxies behave similarly, moving toward these gravitational centers. These movements are not random, but follow a pattern, influenced by the large-scale structure of the universe. As galaxies flow toward dense regions, they help shape and define the cosmic web, a network of filaments and voids that connect everything. The galaxies within these flows are like leaves carried by a river, each moving along its path, but all directed by the underlying current of gravity. This cosmic flow is not only a fascinating phenomenon, but also a key to understanding how the universe evolves. By studying the flow of galaxies, scientists can map out the unseen distribution of mass in the universe, including dark matter, and gain insights into the forces that have shaped the cosmos over billions of years. Redshift surveys are like cosmic maps that have unlocked the secrets of the universe's vast structure. Imagine you're an explorer trying to chart an enormous, unfamiliar landscape, where the distances are so immense that ordinary tools won't suffice. In space, that landscape is the entire cosmos, and redshift surveys are the advanced tools scientists use to map it. The idea behind a redshift survey is straightforward but powerful. When we observe galaxies, the light they emit is often shifted toward the red end of the spectrum, a phenomenon known as redshift. This happens because the universe is expanding, and as galaxies move away from us, their light stretches, shifting to longer, redder wavelengths. The amount of redshift tells us how fast a galaxy is moving away and gives us a clue about its distance from us. Surveys like the Sloan Digital Sky Survey (SDSS) have taken this concept to a monumental scale. They've systematically measured the redshifts of millions of galaxies, creating a 3D map of the universe. It's like taking a giant census of galaxies, not just to count them, but to figure out where they are in relation to one another. By doing this, scientists have revealed the large-scale structure of the universe, the cosmic web of galaxies, clusters, and voids. This map shows not just where galaxies are, but how they are distributed across the cosmos, providing insights into the forces that have shaped the universe over billions of years. Redshift surveys also allow scientists to study cosmic flow patterns, tracking how galaxies move through space under the influence of gravity. This has helped to refine our understanding of the universe's expansion, the distribution of dark matter, and even the overall shape of the cosmos. In essence, redshift surveys have transformed our understanding of the universe from a chaotic scattering of galaxies into a structured and interconnected web, giving us a deeper appreciation of the forces at play on the grandest scales. Baryon acoustic oscillations, BAO, are like cosmic echoes from the universe's infancy, carrying crucial information about how the universe has expanded and evolved over billions of years. To understand BAO, imagine standing in a vast, empty space where you suddenly hear a distant echo. This echo is the remnant of a sound that was once loud and clear, but has since faded over time. In the early universe, right after the Big Bang, the entire cosmos was filled with a hot, dense plasma of particles. In this primordial soup, sound waves rippled through the universe, creating regions of slightly higher and lower density. These sound waves were not like the sounds we hear on Earth, but were more like pressure waves, caused by the interactions between matter and radiation. As the universe cooled and expanded, these waves froze in place when the universe became transparent, about 380,000 years after the Big Bang. The result was a subtle, but measurable pattern of density fluctuations, areas where matter was slightly more or less concentrated. Over billions of years, these patterns of higher and lower density formed the seeds for the large-scale structures we see in the universe today, like galaxies and clusters of galaxies. The imprints of these ancient sound waves, BEOs, are still visible in the distribution of galaxies across the cosmos. When scientists measure the distance between galaxies, they find a slight preference for certain separations, corresponding to the scale of these ancient sound waves. This regular spacing acts like a cosmic ruler, allowing astronomers to measure how the universe has expanded over time. By studying BAOs, scientists can trace the universe's expansion history with incredible precision. This helps them understand the nature of dark energy, the mysterious force driving the acceleration of the universe's expansion. BAOs also offer insights into how matter clumped together to form the cosmic web that defines the structure of the universe. In essence, BAOs are the universe's way of preserving a record of its earliest moments, giving us a window into the past and a tool to understand the universe's ongoing evolution. The Great Attractor is like a gravitational magnet in the cosmos, pulling entire galaxies, including our own Milky Way, toward it. Imagine you're in a crowd, moving along with everyone else, but you can't quite see where you're heading. You just feel an unseen force drawing you in a specific direction. That's what's happening with our galaxy and millions of others as they move toward the Great Attractor. Located about 150 to 250 million light-years away, the Great Attractor lies in a region of space known as the Zone of Avoidance, a part of the sky obscured by the Milky Way's dense plane, making it difficult to observe directly. Despite this, scientists have been able to infer its presence by studying the motion of galaxies around it. These galaxies aren't just drifting through space. They're being pulled by something incredibly massive. This mysterious region exerts a strong gravitational force, suggesting that it contains a massive concentration of matter. However, what exactly makes up the Great Attractor remains unclear. It could be a supercluster of galaxies, a vast amount of dark matter, or perhaps something we don't yet fully understand. The influence of the Great Attractor is so powerful that it's altering the cosmic flow, the movement of galaxies across vast distances. Our entire local group of galaxies, which includes the Milky Way, is moving toward this region at hundreds of kilometers per second. It's as if we're caught in a cosmic current, slowly but surely being drawn toward this enigmatic part of the universe. While we may never reach the Great Attractor, its pull offers a profound reminder of how interconnected the universe is. Even at such vast distances, the gravitational influence of massive structures can shape the motion of galaxies across the cosmos, guiding them along unseen pathways in the grand design of the universe. The cold dark matter, CDM, paradigm is like the blueprint for how the universe built itself from the ground up. Imagine you're watching the early stages of a massive city being constructed. The initial plans might look like scattered points on a map, but over time, those points become the foundation for skyscrapers, roads, and entire neighborhoods. In the universe, those points were tiny fluctuations in the density of dark matter, and they became the seeds for galaxies and clusters. Dark matter is a mysterious substance that doesn't emit or interact with light, making it invisible to us. However, it has mass and therefore exerts gravity, which is the key to its role in shaping the cosmos. The cold in cold dark matter refers to the idea that dark matter particles move slowly compared to the speed of light. This slow movement allowed dark matter to clump together early in the universe's history. These clumps started out as small, random fluctuations in density shortly after the Big Bang. Even though these variations were tiny, over time, gravity amplified them. Imagine tossing a handful of seeds onto the ground. Some seeds land in small depressions, others on flat surfaces. Over time, as rain and wind interact with the landscape, those seeds in the depressions are more likely to grow and thrive. Similarly, in the early universe, regions with slightly more dark matter began to pull in more and more material, growing into the large structures we see today. As these dense regions of dark matter grew, they became the gravitational wells that ordinary matter, gas, dust, and eventually stars fell into. These regions became the galaxies, galaxy clusters, and superclusters that formed the large-scale structure of the universe. The CDM model has been remarkably successful in predicting the distribution of these structures, matching what we observe in the universe today. One of the strengths of the CDM paradigm is its ability to explain not just the existence of galaxies and clusters, but their distribution across vast cosmic distances. The model predicts a universe where galaxies are not uniformly spread out, but are instead clustered together in a web-like structure, with voids in between, exactly what we observe. In essence, The cold dark matter paradigm provides a framework for understanding how the universe went from a nearly uniform state after the Big Bang to the richly structured cosmos we see now. It's like the underlying script that has guided the formation and evolution of everything in the universe, from the smallest galaxies to the largest clusters of galaxies. Cosmic voids are like the empty spaces between islands in a vast ocean, only on an incomprehensibly larger scale. Imagine sailing through a sea dotted with islands. But as you move, you notice there are vast stretches of water where no islands exist, just open, empty space. These empty regions are analogous to cosmic voids, immense, nearly empty areas in the universe that stretch across millions of light years. Voids are the opposite of crowded galaxy clusters. While clusters are packed with galaxies, stars, and dark matter, voids are sparse, with very few galaxies. These vast regions contain only a tiny fraction of the matter found elsewhere in the universe. In fact, the few galaxies that do exist within voids are often isolated, far from the dense, bustling regions of the cosmic web. But cosmic voids are far from being irrelevant empty spaces. They play a crucial role in the universe's large-scale structure. Imagine the universe as a landscape with hills and valleys. The hills represent dense regions filled with galaxies, while the valleys are the voids. Just as water flows downhill, galaxies move away from these underdense regions and toward the denser areas where gravity pulls more strongly. This movement of galaxies away from voids helps to create and define the structure of the universe. Voids, despite their emptiness, shape how galaxies and clusters form and evolve. They act as the cosmic boundaries, pushing galaxies toward the dense filaments and clusters that make up the cosmic web. Voids also offer scientists a unique laboratory for studying the universe. Since they contain so little matter, they are less affected by complex gravitational interactions, making them ideal for testing theories about dark energy and the overall expansion of the universe. By studying voids, scientists can gain insights into the forces that govern cosmic flow and the underlying properties of the universe. In essence, cosmic voids are the quiet, empty spaces that contrast with the busy regions of the universe. Yet they are integral to the grand cosmic design, guiding the flow of galaxies and helping to shape the universe's large-scale structure. Superclusters are like the giant metropolises of the universe, where galaxy clusters come together to form some of the largest structures ever known. Imagine standing on a hill, looking out over a sprawling city where neighborhoods are connected by highways, and those highways link to even bigger cities in the distance. In the universe, superclusters are the cosmic equivalent of those vast cities, with galaxy clusters acting as the neighborhoods. These colossal structures are bound together by gravity, the force that holds the universe's web of galaxies in place. Each supercluster is made up of many galaxy clusters, which are themselves collections of hundreds or even thousands of galaxies. The combined gravitational pull of these clusters is so strong that it keeps them connected, even across hundreds of millions of light years. Superclusters play a vital role in the cosmic flow, the movement of galaxies through space. Because they are so massive, they act like gravitational hubs, influencing the motion of galaxies over vast distances. Just as people in a city gravitate toward its center where resources and opportunities are concentrated, galaxies are drawn toward the dense cores of superclusters. Our own Milky Way is part of the Laniakea supercluster, a structure so immense that it spans over 500 million light years. This supercluster, like others, is a key player in the cosmic flow, directing the movement of galaxies within and around it. The gravitational pull of these superclusters helps to organize the large-scale structure of the universe, guiding galaxies along the filaments of the cosmic web and influencing the formation and evolution of galaxies and clusters. Superclusters also serve as a window into the past. Because they take billions of years to form, studying them allows scientists to trace the history of the universe's expansion and the growth of cosmic structures. They reveal how matter has clumped together over time, shaped by the gravitational pull of dark matter and the expansion driven by dark energy. In essence, superclusters are the universe's grandest constructions, acting as the anchors of the cosmic web and playing a crucial role in the flow and evolution of galaxies across the vast expanse of space. Imagine the universe as a vast, dark ocean, calm at first, but with small ripples across its surface. These ripples represent the tiny differences in density present just after the Big Bang, some regions slightly denser than others. Over time, the pull of gravity caused these denser areas to attract more matter, like how ripples in water might grow if they start to pull in more surrounding water. But unlike water, this process isn't smooth or predictable. Gravity pulled more matter into these dense regions, causing them to grow unevenly and chaotically. This is where the nonlinear growth comes in. As these regions attracted more and more matter, they didn't just grow steadily. They started to warp and twist the surrounding space. Picture these areas as whirlpools forming in the ocean, drawing in material from afar, merging with other whirlpools, and growing stronger, faster, and more complex. On a cosmic scale, this meant that the simple, almost uniform early universe became something far more intricate. The small differences in density exploded into vast galaxies, clusters, and superclusters. Like watching a calm sea suddenly turn into a stormy, churning expanse, where some parts are pulled into vast, spiraling vortices, and others are left as deep, empty voids. The process was anything but straightforward. It involved countless interactions, where regions of higher density exerted their gravitational influence, pulling matter in and triggering the formation of even more massive structures. It's a bit like how, in human society, small inequalities can snowball, leading to the formation of cities and empires from humble beginnings. In essence, the universe's large-scale structure was born from this chaotic, non-linear process, transforming simple beginnings into the complex and awe-inspiring cosmic architecture we see today. The cosmic microwave background, CMB, is like the universe's baby picture, capturing a moment in time when everything was just starting to take shape. Imagine the universe as a hot, dense soup of particles, where everything was so tightly packed and energetic that light couldn't travel freely. It was like trying to see through thick fog, no clear view of anything. Then, around 380,000 years after the Big Bang, something remarkable happened. The universe cooled down just enough for particles to combine and form neutral atoms, allowing light to finally break free. This event, known as recombination, is when the fog lifted and the universe became transparent for the first time. The light that was released at that moment is what we now observe as the CMB. The CMB is not just a uniform glow. When we look at it closely, we see tiny fluctuations in temperature, small variations in this baby picture. These variations, though incredibly slight, are crucial. They represent the early seeds of all the galaxies, stars, and cosmic structures that would later form. It's like looking at a slightly bumpy surface of dough before it's baked. Those bumps hint at where the bread will rise and form different shapes. These temperature fluctuations are the fingerprints of the universe's earliest moments. Over billions of years, they grew under the influence of gravity, evolving into the vast cosmic web of galaxies and clusters that we observe today. Without these early imprints in the CMB, the universe would be a very different place, perhaps even a lifeless, featureless expanse. So when scientists study the CMB, they're essentially peering back in time to when the universe was just beginning to develop the complexities that would eventually lead to everything we see around us, including life itself. The Hubble flow is like the universe's grand dance, where every galaxy is a dancer moving away from the others as the stage itself expands. Imagine you're standing on the surface of a giant balloon. As the balloon inflates, every point on it moves away from every other point. Not because the points themselves are moving, but because the surface of the balloon is stretching. This is similar to how the universe is expanding, causing galaxies to drift apart. Hubble's law describes this expansion. It tells us that the farther away a galaxy is, the faster it appears to be moving away from us. It's like being in a crowd that's spreading out. The people farthest from you are moving away faster than those closer by. But this cosmic dance isn't perfectly smooth. Just like how individual dancers might have their own moves, galaxies also have their own peculiar velocities. These are small, extra motions caused by local gravitational influences, like nearby galaxies pulling on each other. For example, while the general expansion might push two galaxies apart, their mutual gravitational attraction could cause them to move towards each other, creating a complex pattern of motion. So, while the Hubble flow sets the overall rhythm of the universe's expansion, each galaxy also has its own unique steps in this cosmic dance, influenced by the gravitational forces of its neighbors. It's a delicate balance between the broad sweep of the universe's expansion and the local gravitational tugs, all playing out on the grandest stage imaginable. Now, let's zoom in and look at one of the key players in this grand cosmic performance, the Laniakea supercluster. This is where our Milky Way and countless other galaxies call home. Picture Laniakea as a vast, sprawling neighborhood in the universe's city, where galaxies cluster together in a gigantic, interconnected web of gravitational influence. It's a supercluster that stretches across about 500 million light-years, showcasing the grand scale of cosmic structure and the intricate patterns of movement we've been discussing. The Laniakea supercluster is a breathtaking reminder of how interconnected our universe truly is. Imagine standing on a beach, looking out at the vast ocean, knowing that beneath the surface, countless currents and tides are constantly at work, shaping the water's movement. The Laniakea supercluster is like that ocean, an immense, interconnected network of galaxies, all influenced by the gravitational currents that bind them together. This supercluster is home to over 100,000 galaxies, including our own Milky Way, and stretches across more than 500 million light-years of space. The name Laniakea, which means immense heaven in Hawaiian, reflects the awe-inspiring scale of this cosmic structure. Within this vast region, galaxies aren't just scattered randomly. They're moving along paths defined by the gravitational pull of massive structures like the Great Attractor. But Laniakea is more than just a collection of galaxies. It's a dynamic, living structure, with galaxies streaming along invisible lines of force toward various centers of gravity. These movements are like rivers flowing toward the ocean, guided by the unseen forces that shape the universe on the largest scales. What makes the Laniakea supercluster truly fascinating is how it challenges our understanding of the universe's architecture. It redefines the boundaries of what we consider a galaxy cluster, showing us that these structures are far more interconnected than we once thought. The galaxies within Laniakea are part of a vast, cosmic web, linked by gravity in ways that are still not fully understood. For us on Earth, it's humbling to realize that our galaxy is just one small part of this immense supercluster. Laniakea serves as a reminder of our place in the universe, not just as inhabitants of a single planet or a single galaxy, but as part of a vast, interconnected system that spans hundreds of millions of light years. In exploring Laniakea, we're not just mapping the cosmos, we're also seeking to understand the fundamental forces that shape the universe. It's a journey that pushes the limits of human knowledge and sparks a sense of wonder about the intricate and immense structure of the universe we call home. Imagine standing on Earth, looking up at the night sky. Every star you see belongs to our galaxy, the Milky Way, which itself contains around 100 billion stars. But the Milky Way is just one of over 100,000 galaxies in the Laniakea supercluster. Now consider the distance between galaxies. Light, traveling at 186,000 miles per second, takes 25,000 years just to cross our galaxy. Laniakea spans a distance of over 520 million light-years. To put that in perspective, if you could travel at the speed of light, it would take you over 520 million years to go from one end of Laniakea to the other. In this vast expanse, galaxies aren't scattered randomly. They're connected by gravity, forming a massive structure that holds all these galaxies together. Our Milky Way is just a tiny part of this immense web. When you look at the sky, you're not just seeing stars or even just our galaxy. You're peering into a tiny corner of this supercluster, a structure so vast that it's almost impossible to fully grasp its scale. This scale puts human existence into perspective. Our entire history, our planet, our solar system, everything we know resides in just a tiny speck of the Laniakea supercluster. This isn't just about the size. It's about our place in the universe, where even the largest things we can imagine are just small parts of something much bigger. The Laniakea supercluster is not just a random gathering of galaxies floating in space. It's a massive, interconnected system where gravity plays the central role. Imagine a vast network where everything is linked by invisible threads, pulling and tugging on each other. These threads are the gravitational forces that bind over 100,000 galaxies together in a delicate but powerful balance. Our galaxy, the Milky Way, is part of this intricate web. It's like being in a small neighborhood within a sprawling city. Just as neighborhoods connect through roads and highways, galaxies within Laniakea are connected through gravitational pull. This pull is what keeps everything in place and moving together as a unified whole. Now, within Laniakea, there are smaller clusters of galaxies, one of which is the Virgo supercluster. Think of it as a district within the city, and our Milky Way is one of the many houses in this district. The Virgo supercluster is just a part of the much larger Laniakea, which means that everything we know, our galaxy, our solar system, our planet, is part of this immense cosmic structure. This connectivity is what makes Laniakea more than just a collection of galaxies. It's a living, dynamic system where each galaxy, including our own, moves in response to the gravitational forces of its neighbors. We're not isolated in space. We're part of a vast, interconnected cosmic community, moving through the universe together. Imagine the universe as a giant spider's web, but instead of silk threads, it's made of galaxies and dark matter. This is the cosmic web, a vast network that spans the entire universe, connecting everything within it. Each thread of this web is made up of galaxies, and where the threads intersect, you find dense clusters of galaxies, like knots in the web. Laniakea is one of these massive knots, a supercluster where thousands of galaxies are gathered together, all held in place by the invisible pull of gravity and dark matter. But Laniakea isn't isolated. It's connected to other superclusters through these cosmic filaments, stretching out for billions of light years. These connections mean that what happens in one part of the universe can influence distant regions through the gravitational ties that bind them. This interconnectedness is like the relationships in a community. Just as people are connected through families, friends, and communities, galaxies are connected through this cosmic web. They interact, move, and even collide with one another, influenced by the gravitational pulls that stretch across vast distances. In this web, nothing exists alone. The Milky Way, for instance, isn't just floating in space. It's part of a complex system of relationships that extend far beyond what we can see. The cosmic web reveals that our galaxy is part of a much larger, interconnected structure, where every galaxy, including ours, plays a role in the larger cosmic dance. This vast network shows that in the grand scale of the universe, everything is connected, from the smallest star to the largest supercluster. Before the discovery of Laniakea, astronomers thought of superclusters as separate islands in the vast ocean of space, each with its own set of galaxies. These boundaries were drawn based on the idea that each supercluster was an isolated entity, distinct from its neighbors. But when Laniakea was discovered, it changed how we understand these cosmic structures. Imagine discovering that the islands you thought were separate are actually part of a much larger continent. Laniakea showed that what we once thought were independent superclusters are actually connected by gravitational forces, forming a single, massive structure. This discovery was like redrawing the map of the universe. The borders that once seemed clear were blurred as astronomers realized that these superclusters are not isolated but interconnected. The Milky Way, for example, isn't just part of the Virgo supercluster. It's also part of the much larger Laniakea supercluster, which includes other groups of galaxies we once thought were separate. This redefinition is significant because it changes how we see our place in the universe. It's as if we discovered that the neighborhood we live in is part of a much larger city that we never knew existed. Laniakea's discovery revealed that the universe is more interconnected and unified than we ever imagined, leading us to rethink the boundaries we once took for granted. Dark matter is like the unseen force holding the universe together, and it plays a crucial role in the existence of the Laniakea supercluster. Imagine trying to understand the layout of a city without being able to see the roads that connect everything. You'd see the buildings and neighborhoods, but you'd miss the network that ties it all together. Dark matter is like those roads. It's invisible to us, but it's what keeps galaxies and superclusters like Laniakea in place. Without dark matter, the galaxies in Laniakea wouldn't have the gravitational glue they need to stay bound together. They'd drift apart, and the structure of Laniakea would unravel. But dark matter, which doesn't emit light or energy, creates the gravitational pull that holds everything in place, from individual galaxies to the entire supercluster. What makes this even more intriguing is that we don't really know what dark matter is. We can't see it, touch it, or even detect it directly. Yet, we know it's there because we see its effects everywhere in the universe. It's like trying to solve a puzzle with a piece missing. You can see the shape of the hole and know something belongs there, but you're not sure what it looks like. In the case of Laniakea, dark matter is that missing piece. It's what allows this vast supercluster to exist as a cohesive structure. The fact that we still don't fully understand dark matter adds to the mystery and wonder of the universe. It reminds us that there are still profound questions left to answer, even about something as fundamental as what holds the cosmos together. The name Laniakea comes from the Hawaiian language, where Lani means heaven and Akea means spacious or immense. When you put those words together, Laniakea translates to immense heaven, a fitting description for a structure as vast as this supercluster. Imagine standing on a quiet beach in Hawaii, looking up at the night sky. The stars stretch out endlessly above you, and you feel a deep sense of awe at the sheer scale of the universe. This feeling of wonder is what the name Laniakea captures. It's not just a scientific term. It's a reminder of the vastness of the cosmos and our place within it. The choice of a Hawaiian name is also significant because it connects modern astronomy with ancient traditions. The Polynesians, including the Hawaiians, were master navigators, using the stars to find their way across the vast Pacific Ocean. Naming the supercluster Laniakea honors that legacy of exploration and wonder, linking our quest to understand the universe with the timeless human drive to explore the unknown. In a way, Laniakea is more than just a name. It's a poetic expression of the awe that this immense structure inspires. It invites us to think about the universe not just as a collection of galaxies, but as a vast, almost sacred space that stretches beyond our comprehension. At the heart of this awe-inspiring region lies an enigmatic force known as the Great Attractor. This mysterious gravitational anomaly is drawing galaxies, including our own Milky Way, toward it at incredible speeds, reshaping our understanding of the cosmos. Back in the 1970s and 1980s, astronomers stumbled upon something that didn't quite fit with their understanding of the universe. They noticed that galaxies, including our own Milky Way, were moving toward a particular region in space at speeds that didn't make sense given what they knew at the time. This wasn't just a casual drift. It was more like an urgent rush, as if something massive was calling them. The clues came from studying cosmic microwave background radiation, the afterglow of the Big Bang, which showed that our galaxy was moving in a way that suggested something huge and unseen was pulling it along. This unseen force was traced back to a region about 150 million light-years away, somewhere in the direction of the Centaurus and Norma constellations. They named it the Great Attractor, a fitting title for something with such a powerful grip on its cosmic surroundings. But even after pinpointing its location, the nature of this force remains a topic of lively debate. It's not a single, colossal object like a black hole or a giant galaxy. Instead, it's a densely packed area of space brimming with mass, probably a mix of galaxies, galaxy clusters, and that ever-mysterious dark matter that we know is out there but still struggle to fully comprehend. What makes the Great Attractor even more intriguing is its placement in what's known as the zone of avoidance. This part of the sky is blocked from our direct view by the Milky Way's thick disk of stars, gas, and dust. It's like trying to see something on the other side of a foggy window. You know it's there because of its effects, but you can't get a clear look at it. Astronomers have to rely on other methods, like X-rays and radio waves, to catch glimpses of what's hidden in this obscured region. The Great Attractor isn't just a curious anomaly out in space. It's having a direct impact on us. Our entire local group of galaxies, which includes the Milky Way and Andromeda, is being pulled toward this region at breakneck speed, about 600 kilometers per second. But here's where things get really interesting. This movement is just one part of a much larger story. The Milky Way is also influenced by other massive structures, like the Virgo cluster and the Shapley supercluster, the latter of which might be the real heavyweight in this cosmic tug-of-war. Recent findings suggest that the Shapley supercluster, even further away and much larger than the Great Attractor, could be the ultimate force behind the scenes, pulling not just us, but the Great Attractor itself along with it. This adds another layer of complexity to our understanding of the universe. The Great Attractor might be a major player, but it could also be just a stepping stone on an even grander journey through the cosmic web of superclusters that make up the large-scale structure of the universe. Despite all the research, the Great Attractor still holds onto many of its secrets. We're left with more questions than answers. What exactly is it made of? How much of its mass is dark matter? And what does it mean for the future of our galaxy as we continue to be drawn toward it? As technology advances, particularly in the areas of X-ray and infrared astronomy, we might get closer to uncovering these mysteries. But for now, the Great Attractor stands as a symbol of the vast, unseen forces that shape our universe. A reminder that there's still so much out there waiting to be understood. The Great Attractor's gravitational pull is like a cosmic undertow, an invisible force that subtly but irresistibly tugs at everything in its reach. Picture it this way. Imagine you're standing on the shore, feeling the pull of the ocean as the waves recede. Only in this case, the waves are entire galaxies, and the ocean is the vast expanse of the universe. This force is not something we can see or touch, but we can measure its effects. Galaxies, including our own Milky Way, are not just drifting aimlessly through space. They're being drawn towards a particular point, almost as if they're being lured by an unseen hand. The distances involved are mind-boggling, millions of light years across. But even over such vast expanses, the pull of the Great Attractor is strong enough to accelerate entire galaxies to speeds that defy easy explanation. This isn't just a casual pull. It's like being caught in a slow but powerful current that you can't swim against. The gravitational force at play here is on a scale that's hard to fathom, because it's not just influencing a star or two, it's altering the paths of galaxies that contain billions of stars. And this pull isn't happening in an instant. It's a slow, steady drag that's been ongoing for millions of years, quietly redirecting the motion of galaxies as if they were leaves floating on a vast cosmic river. The incredible thing is that this force is being exerted from such a great distance, yet it still manages to have a noticeable effect on the Milky Way and many other galaxies. It's as if space itself is slightly warped in the direction of the Great Attractor, and everything within that distorted region is being nudged along that path, no matter how far away it is. Even though we can't see the Great Attractor directly, we can observe its influence through the way galaxies behave, how they're not just moving away from each other, as the expansion of the universe would suggest, but also moving sideways, pulled by this massive unseen structure. It's a reminder of the sheer power of gravity, especially when it's wielded by something as massive and mysterious as the Great Attractor, quietly steering the course of countless galaxies over unimaginable distances and timescales. The Great Attractor sits in one of the universe's most secretive corners, concealed behind a thick veil of gas, dust, and countless stars that make up the Milky Way. This area is known as the Zone of Avoidance, and it's aptly named because it's almost impossible for us to see what's hiding there using regular telescopes. Imagine trying to peer through a dense forest on a foggy night. You know something is out there, but the trees and mist block your view, turning everything into vague, shadowy shapes. In the case of the Great Attractor, the fog isn't water vapor, but the Milky Way itself. The plane of our galaxy is packed with stars, clouds of gas, and floating particles of dust that scatter and absorb light, especially the kind of light our eyes can see. This means that even though the Great Attractor is out there, its true nature is hidden from us, shrouded by the very galaxy we live in. When astronomers look in the direction of the Great Attractor using visible light, they see the glow of millions of stars in the Milky Way, not the structure they're searching for. It's like staring into a bright light when you're trying to see what's beyond it. The glare overwhelms everything else. This makes the Great Attractor incredibly elusive, more like a ghost of a structure than something solid and observable. But just because it's hidden doesn't mean it's invisible to all forms of observation. Astronomers have found ways to peek through the Milky Way's veil by using wavelengths of light that can pass through the dust. Things like X-rays, radio waves, and infrared light. These tools let them catch glimpses of what's lurking in the zone of avoidance. It's a bit like using night vision goggles to see in the dark. Suddenly, what was hidden starts to become clearer, revealing that the Great Attractor is indeed a massive concentration of matter, even if we can't yet fully map it out. This hidden aspect adds to the mystery and allure of the Great Attractor. It's out there, pulling entire galaxies toward it, yet it remains concealed from our direct gaze, challenging us to uncover its secrets with every new technological advance. The fact that something so influential can remain so hidden is a reminder of how much we still have to discover in the cosmos, and how the universe often keeps its most intriguing secrets just out of reach. The Great Attractor sits at an almost unfathomable distance from us, about 150 million light-years away. To put that into perspective, if you could travel at the speed of light, it would take you 150 million years to reach it. But despite being so far away, its gravitational influence extends across hundreds of millions of light years, shaping the movement of galaxies in its grasp like a puppeteer pulling on invisible strings. Imagine a force so powerful that it can affect objects separated by almost incomprehensible distances. The Great Attractor is like a distant magnet, exerting a pull that stretches out across the vastness of space. This force doesn't just tug on a few nearby galaxies. It reaches out across an enormous region of the universe known as the Laniakea Supercluster, which includes our own Milky Way and thousands of other galaxies. What's astonishing is how this force, originating from a spot so far away, can still have a noticeable impact on galaxies hundreds of millions of light years apart. It's like dropping a stone into a pond and watching the ripples spread out. But on a cosmic scale, the ripples are gravitational waves influencing the paths of galaxies far and wide. These galaxies, spread out over such a vast area, aren't just drifting aimlessly. They're all subtly altering their courses, drawn toward this mysterious, distant point. The Great Attractor's influence is a quiet but powerful force, guiding the movement of entire clusters of galaxies. Even though these galaxies are separated by immense distances, the pull is strong enough to create a pattern of motion that astronomers can observe and measure, showing just how interconnected the universe really is. This gravitational pull, stretching across such an enormous expanse of space, is a reminder of the vastness of the universe and the incredible forces at work within it. Even across distances that seem beyond comprehension, the Great Attractor manages to assert its influence, shaping the cosmic landscape on a scale that's hard to imagine, yet undeniable in its effects. The Great Attractor isn't just one enormous thing floating out there in space. It's more like a tangled web of different cosmic elements all clustered together. Imagine standing at the edge of a dense, bustling city. From a distance, it might look like one big blur of lights and movement. But as you get closer, you start to see that it's made up of countless buildings, streets, and people, all interconnected yet distinct. That's what the Great Attractor is like, but on a scale that stretches across millions of light years. This region is packed with galaxies, each one a collection of billions of stars, along with galaxy clusters that group these galaxies together. But what makes it even more complex is the presence of dark matter, the mysterious substance that doesn't emit light but has a significant gravitational pull. Dark matter is like the unseen scaffolding holding everything together, adding to the mass and influence of the Great Attractor without us being able to directly observe it. The complexity of this structure makes it difficult to fully grasp with our current understanding of the universe. It's not a neat, tidy object like a star or a planet that we can easily study. Instead, it's this sprawling, interconnected mass that challenges the way we think about the large-scale makeup of the cosmos. It's like trying to understand a city by only looking at a few streets at a time. You know there's more to it, but piecing it all together is a monumental task. Astronomers are still working to unravel this cosmic puzzle, trying to map out the different components and understand how they all fit together. The Great Attractor's complexity reminds us that the universe is not just made of simple, isolated objects. It's a vast, intricate web where everything is connected, sometimes in ways that are still beyond our full understanding. This region forces us to rethink what we know about how matter is distributed across the universe and how these massive, interconnected structures come to be. The Great Attractor, as immense and powerful as it is, might just be one piece of a much larger cosmic puzzle. It's like finding a giant knot in a sprawling, intricate network of threads and realizing that this knot is connected to an even bigger and more complex pattern. In this case, the threads are galaxies and clusters of galaxies, and the larger pattern is the Shapley supercluster, one of the most massive concentrations of matter we've ever discovered. Imagine the universe as a giant, three-dimensional web with strands stretching across vast distances. At the points where these strands intersect, you have nodes, dense regions where galaxies and matter cluster together. The Great Attractor is one of these nodes, a particularly massive and influential one, but it's connected to other nodes by the gravitational pull that threads through the entire structure. The Shapley supercluster is like the central hub of this web, a massive, sprawling collection of galaxies that dwarfs even the Great Attractor. If you think of the Great Attractor as a city, then the Shapley supercluster is the vast metropolis that it belongs to, with countless other cities, galaxy clusters, all linked together in a complex and dynamic network. What's fascinating is how this suggests that the Great Attractor isn't the final stop on the cosmic journey of our galaxy, but rather just one significant point along the way. The gravitational pull we feel from the Great Attractor might actually be part of an even larger gravitational force, one that's drawing entire regions of the universe toward the Shapley supercluster. It's like being on a road trip where each city you pass through is just part of a much longer journey to an even more massive destination. This realization changes how we see our place in the universe. We're not just part of a galaxy moving through empty space. We're part of a vast and interconnected web of matter that stretches across unimaginable distances. The Great Attractor, powerful as it is just one node in this web, a reminder that the universe is far more intricate and interconnected than we once imagined. It's a humbling thought, knowing that even the most massive structures we can observe are themselves part of something even larger and more complex, all tied together by the invisible threads of gravity that shape the cosmos. Imagine standing still in your room, feeling safe and grounded, yet the reality is far more dynamic and awe-inspiring. You, along with everything around you, the chair, the walls, your entire home, are moving through space at an unimaginable speed, caught up in a vast, cosmic dance that stretches far beyond our comprehension. This motion isn't just about the Earth rotating on its axis or orbiting the Sun. It goes much deeper to the level of our entire galaxy, the Milky Way, and its neighbors in the local group. We are all part of a grand journey, pulled relentlessly towards an unseen destination known as the Great Attractor. This colossal region of space, some 150 to 250 million light-years away, exerts an extraordinary gravitational pull on everything within its reach. The speed at which we are being drawn toward the Great Attractor is mind-boggling, around 600 kilometers per second, or about 1.3 million miles per hour. This means that as you sit reading these words, you are hurtling through space at a speed that dwarfs anything we experience in our everyday lives. This motion is so vast and complex that it's beyond any sensation we can feel, but it's happening nonetheless. What makes this even more fascinating is that the Great Attractor is shrouded in mystery. We can't directly see it because it's hidden behind a thick curtain of gas and dust in the plane of the Milky Way. We only know of its existence because of the way it tugs on galaxies, pulling them in its direction. It's as if we're all being led toward a destiny we can't fully understand, drawn by a force that operates on a scale far beyond human experience. This relentless motion adds a profound layer to our existence. While we go about our daily lives, working, laughing, dreaming, we're all passengers on this cosmic journey, moving as part of a much larger narrative. This perspective reminds us of our place in the universe, not as static beings, but as participants in a vast, ever-moving cosmos. Our lives, so rooted in the here and now, are inextricably linked to this grand movement, where even the largest structures in the universe are constantly in motion, shaped by forces we are only beginning to comprehend. In the vastness of the universe, where light from distant stars travels for millions of years to reach us, there exists a profound mystery, one that challenges our understanding of reality itself. This mystery is dark matter, an elusive substance that neither emits nor absorbs light, making it invisible to even the most advanced telescopes. Yet, it is thought to be the dominant force behind much of the universe's structure, including the enigmatic Great Attractor. Imagine walking through a fog so thick that you can't see the path ahead, but you feel a strong pull guiding your steps. You know something powerful is out there, but it remains hidden from view. This is what scientists experience when they study the Great Attractor. Despite being obscured by clouds of gas and dust, this colossal region of space exerts a gravitational force so strong that it influences the motion of entire galaxies, including our own Milky Way. But what makes up this mass? A significant portion is believed to be dark matter. Dark matter is a substance that defies our usual ways of seeing the universe. We can't observe it directly, yet we know it's there because of the way it interacts with the visible matter we can see. It's like trying to understand the wind by watching how it moves the leaves on a tree. We can't see the wind, but we know it's real because of its effects. Similarly, dark matter doesn't glow, reflect, or block light, but it exerts a gravitational pull that shapes the structure of the cosmos. When scientists look at the Great Attractor, they see galaxies moving toward a point in space at incredible speeds. The gravitational pull required to move such enormous masses so quickly suggests that there's a lot more mass there than what we can account for with visible matter alone. This is where dark matter comes into play. It's thought to make up the bulk of the Great Attractor's mass, adding a layer of complexity and mystery to an already perplexing phenomenon. What makes this so intriguing on a human level is that dark matter forces us to confront the limits of our knowledge. We live in a universe where most of the mass is composed of something we can't see or touch, something that doesn't fit neatly into our current understanding of physics. It's a humbling reminder that despite all our technological advances, there are still fundamental aspects of reality that elude us. Yet, this mystery also sparks our imagination. The idea that the universe is filled with this unseen substance that shapes everything from the formation of galaxies to the movements of vast cosmic structures invites us to keep exploring, to keep questioning. It's a call to curiosity, to wonder about what else might be out there hidden in the fabric of the universe, waiting to be discovered. So, as we journey through space, drawn toward the Great Attractor, we're also moving through a universe filled with dark matter, an invisible force that binds the cosmos together. It's a mystery that challenges us to look beyond the visible, to seek understanding in the unseen, and to embrace the unknown as a fundamental part of our reality. In the realm of science, where curiosity drives exploration, few mysteries are as compelling as the Great Attractor. For decades, astronomers and cosmologists have been drawn to this enigmatic region of space, much like it draws entire galaxies toward itself. Yet, despite years of research and countless hours spent peering into the cosmos, the true nature of the Great Attractor remains one of the universe's most stubborn secrets. Imagine a puzzle where the pieces don't quite fit, where the image you're trying to form remains incomplete no matter how hard you try. This is the challenge faced by scientists who study the Great Attractor. They know it's there. Its gravitational influence is undeniable, tugging at galaxies and altering their paths. But what exactly it is remains shrouded in mystery. Is it a massive supercluster of galaxies? A dense region filled with dark matter? Or something entirely unknown? The answer remains elusive. This uncertainty isn't for lack of effort. Over the years, researchers have employed some of the most advanced tools available, from powerful telescopes to sophisticated computer simulations, all in an attempt to uncover the Great Attractor's secrets. But the more they learn, the more complex the picture becomes. The Great Attractor isn't just a single object. It's part of a much larger structure, interconnected with other massive formations in the universe. each one influencing the others in ways we are only beginning to understand. What makes this mystery so profoundly human is the persistence it demands. The study of the Great Attractor pushes scientists to the very limits of what we know and then beyond into the realm of the unknown. It's a reminder that despite all our advances, there are still vast regions of the universe and of knowledge itself that remain unexplored. This quest to understand something so far beyond our everyday experience is driven by the same curiosity that led early humans to look up at the stars and wonder what lies beyond. Yet, with all our questions, the Great Attractor also confronts us with a humbling reality. Some answers may take generations to uncover, if they can be uncovered at all. The ultimate fate of the Great Attractor, whether it will continue to pull galaxies into its grasp or if some other cosmic event will change its course, remains an open question. This uncertainty doesn't deter scientists. Instead, it motivates them to keep asking, keep probing, and keep expanding the boundaries of our understanding. In the end, the study of the Great Attractor is not just about solving a cosmic puzzle. It's about the journey of discovery itself. It's about embracing the unknown and the challenges that come with it, knowing that every step forward, no matter how small, brings us closer to understanding the universe we inhabit. And in that journey, there's a reflection of our own human experience, a reminder that the pursuit of knowledge is as much about the questions as it is about the answers. In the vast expanse of the universe, where galaxies drift like islands in a cosmic ocean, the Great Attractor stands as a powerful force, shaping the motion of these immense structures. This force isn't just a local phenomenon. It's part of a much larger tapestry of gravitational influences that govern the behavior of galaxies on a grand scale. By studying the Great Attractor, scientists hope to uncover clues about the future trajectory of galaxies and, ultimately, the fate of the universe itself. Imagine watching a leaf floating down a river, carried by currents you can't see but know are there. The path of the leaf, its twists and turns, hints at the hidden forces beneath the surface. Similarly, the motion of galaxies toward the Great Attractor suggests the presence of larger, unseen forces that are guiding the movement of entire clusters of galaxies. Understanding these forces could offer profound insights into the destiny of the universe. If the Great Attractor is part of an even larger structure, its influence might extend far beyond what we currently understand, potentially affecting the way galaxies will interact in the distant future. This could help answer some of the most fundamental questions about the universe. Will galaxies continue to cluster together, forming ever larger structures? Or will they eventually drift apart, leaving the cosmos a more isolated and lonely place? For scientists, this is more than just an academic pursuit. It's a quest to understand our place in the grand scheme of things. The fate of the universe, after all, is not just about distant galaxies. It's about the ultimate destiny of everything we know, including our own Milky Way. The forces at work in regions like the Great Attractor are the same forces that will determine whether the universe continues to expand forever, tearing galaxies apart in the process, or whether it might one day collapse back in on itself. In this sense, the study of the Great Attractor is deeply connected to our own future. It challenges us to think on a cosmic scale, to consider how the movements of galaxies today might shape the universe billions of years from now. This inquiry taps into something profoundly human, the desire to understand where we come from and where we're headed, not just as individuals or a species, but as part of the universe itself. By unraveling the mysteries of the Great Attractor, we take a step closer to answering the ultimate questions about the fate of the cosmos and, by extension, our place within it. The Great Attractor stands as a powerful symbol of the universe's vast scale and bewildering complexity. It's a force so immense that it influences the movement of galaxies across hundreds of millions of light years, yet it remains hidden from direct observation. In this, it reminds us of how much of the cosmos is still shrouded in mystery, challenging our understanding and pushing the boundaries of what we know. Consider for a moment the sheer size of the universe. We live on a tiny planet, orbiting a single star among billions in our galaxy, which is just one of countless others. The Great Attractor, with its incredible gravitational pull, operates on a scale that dwarfs our everyday experiences. It's a reminder that the universe is far larger and more complex than we can easily comprehend. The forces at play in the Great Attractor, while invisible and distant, have real consequences for the galaxies they affect, including our own. This sense of scale can be humbling. It forces us to confront the limits of our knowledge and the fact that there is so much about the universe that remains beyond our grasp. The Great Attractor, in its enigmatic nature, exemplifies the puzzles that scientists face as they attempt to unravel the cosmos' deepest secrets. Despite all our advances, despite the powerful telescopes and intricate theories, there are still phenomena that elude our understanding. Yet this complexity also speaks to the incredible richness of the universe. The fact that something as massive as the Great Attractor exists, and that it can exert such a profound influence while remaining largely hidden, highlights the intricate and interconnected nature of the cosmos. It challenges us to think in new ways, to develop new tools, and to push our understanding to new heights. For those who study the universe, the Great Attractor is more than just a physical phenomenon. It's a symbol of the endless quest for knowledge. It reminds us that the universe is not a simple, orderly place, but a vast, dynamic system full of surprises. And it's in the pursuit of these mysteries that we grow, not just in our scientific understanding, but in our appreciation of the complexity and wonder of the world we live in. In the end, the Great Attractor challenges us to embrace the unknown, to accept that there are forces at work in the universe that are far beyond our current understanding, and to continue seeking answers in a cosmos that is as beautiful as it is bewildering. It's a testament to the human spirit's drive to explore, to question, and to expand the horizons of what we know. The Great Attractor is one of those cosmic mysteries that remind us how small and young we are in the grand scheme of things. It's a phenomenon that not only sparks curiosity, but also challenges our understanding of the universe. Imagine looking up at the night sky, filled with countless stars, and realizing that beyond what you can see, there are forces at play that we barely comprehend. Forces like the Great Attractor. This massive region of space, hidden in a zone of avoidance, is blocked from our view by the dust and gas of the Milky Way. It's almost as if the universe is keeping a secret from us, placing a cosmic veil over one of its most intriguing features. Despite this, we know it's there because of the powerful gravitational pull it exerts on entire clusters of galaxies, including our own. Galaxies are speeding toward it at an astonishing 600 kilometers per second, and yet we can't fully see or understand what's drawing them in. The Great Attractor isn't just a solitary enigma. It's part of something much larger, the Laniakea Supercluster, a vast network of galaxies interconnected across unimaginable distances. It's humbling to think that our Milky Way is just one tiny part of this colossal structure, influenced by forces far beyond our everyday experiences. Even with all our technological advances, the exact nature of the Great Attractor remains a puzzle. We believe it's composed of a massive concentration of galaxies and dark matter, but there's so much we don't know. Dark matter, an invisible substance that makes up most of the universe's mass, adds another layer of mystery. It's like trying to solve a puzzle where most of the pieces are missing, yet the picture is still shaping the world around us. What's particularly fascinating, and a bit unsettling, is that the Great Attractor's pull is strong enough to influence the future of galaxies, including our own. Over billions of years, this force could alter the course of galaxies, reshaping the structure of the universe itself. It's a reminder that the universe is in constant motion, governed by forces we're only beginning to understand. Despite decades of study, the Great Attractor continues to challenge scientists. It's a symbol of the vast unknowns that still exist in cosmology. Each discovery about it raises more questions, pushing the limits of what we know and inviting us to explore further. But the Great Attractor isn't the end of the story. Beyond it lies the Shapley Supercluster, an even larger and more massive structure, adding to the complexity of the cosmic landscape. It's as if the universe is layered with mysteries, each one more challenging than the last. Even the subtle effects of the Great Attractor can be felt on a cosmic scale. The motion of our galaxy toward it creates a tiny but measurable difference in the cosmic microwave background radiation, the the afterglow of the Big Bang. This slight temperature variation gives us clues about the forces shaping our galaxy's journey through the universe. In the end, the Great Attractor is more than just a scientific puzzle. It's a reminder of how much we have yet to learn. It challenges us to push beyond the boundaries of our knowledge and to embrace the vast, unexplored universe that lies beyond. It's a symbol of the complexity and scale of the cosmos, and of our ongoing quest to understand the forces that shape our reality. When we step back and look at the universe, from the mysterious pull of the Great Attractor to the sprawling expanse of the Laniakea supercluster, and the intricate dance of cosmic flow that weaves it all together, we're reminded of just how small we are in the grand scheme of things. Yet, within this vastness, there's something deeply human about our quest to understand it all. We're drawn to the unknown, just as galaxies are drawn across the universe, compelled to explore, to ask questions, and to find our place in this immense cosmic web. These discoveries don't just expand our knowledge. They connect us to something larger, reminding us that even in the boundless universe, our curiosity and wonder give us a unique place in the story of it all. If you've enjoyed this journey through the cosmos with Quiet Universe, from the pull of the Great Attractor to the wonders of Laniakea, why not join us for more? Like the galaxies drawn together by cosmic flow, you can be part of this expanding universe of exploration. Thank you for watching, and don't forget to like the video and subscribe, because there's always more to discover, and we'd love to have you along for the ride.